Hello there, Mr. Sutton here, bringing you this lesson on integration with respect to the y-axis. Specifically, we are going to be solving area and volume problems using integration with respect to y. So let's talk a little bit about integration with respect to y. First off, to review what we've been doing so far. Thus far, we've been integrating with respect to x, which means we're adding vertical distances together. You've got a bunch of super skinny rectangles and added them together left to right. In this lesson, we're going to be integrating with respect to y, which is to say we're going to be integrating sideways based on horizontal distance. So let's say that we have some bounded region with two functions, and instead of having vertical rectangles that we're adding together, you're doing horizontal rectangles. To compare this with integration with respect to x, the old way of doing things, x integration, you have an integral that is going from the leftmost x value to the rightmost. We're going left to right on the bounded region. And we're doing top function minus bottom function, upper function minus lower function. And since this is a function of x that we're integrating on this, dx was our differential in this situation. Now, y integration changes all of this, and you kind of have to turn your head sideways to really appreciate this. With y integration, you're not going from left to right anymore. You're going from lower y values to higher y values, which is to say you're going from bottom to top, from lowest to highest y values. And you can't really do upper minus lower anymore because y integration is doing things horizontally in terms of what we're adding together. So now we need to do rightmost function minus leftmost function. And since we're integrating with respect to y, our differential is going to be dy instead of dx. In fact, if you take a look at this graph a little more closely, look at this, g of y, f of y. These are both functions that take y as an input and x as the output. So that's how we're changing things today. So let's take a look at our first example. They want us to find the area of the region enclosed by the square root of x and x minus 2 and y equals 0. Take a moment to graph that on Desmos. Alright, so let me go ahead and graph it on mine as well. So we have f of x equals square root of x. So there's our square root function, and g of x equals x minus 2, and we have the line y equals 0, which is just the x-axis. So this is our region in here that we're trying to figure out the area of that, so this enclosed region. Now there's a couple ways to do this problem. If we were going to try to do this the old-fashioned way, going left to right and adding up these distance strips, that would work fine, except that although we have the same top function the whole time, our bottom function changes where this line is crossing the x-axis. So two integrals would be required when integrating vertically with respect to the x-axis due to this function change happening at 2. And you could do two different integrals, and that's just fine. However, what if we think about this as not a vertical sort of distance strips, but horizontal distance strips? We only need one integral if we're doing this with respect to y. There's only one rightmost and leftmost function. The key, the trick on this though, is before you can do that, you're going to have to express these functions in terms of y. So you would have to write them as f of y equals something in terms of y. If you're wondering how to do that, just imagine what you would do if you were trying to get x by itself. Because just like f of x is really just a fancy name for y, f of y is just a fancy name for x. So if you can isolate x, you've basically got those functions. The other piece of it is when you're doing your limits of integration, we can't use like x values anymore. We need to find the intersections now as y values in order to get our limits of integration. So with all that in mind, pause the video and see if you can figure out how to integrate this thing one way or another, but try the with respect to y part of it. Alright, so rewriting my functions. To rewrite f of x equals square root of x, if I wanted to get x by itself, I would have to square both sides. So I could also write this as x equals, or f of y equals y squared. And over here, the g function, if I add 2 to the other side, I can write f of y equals y plus, or g of y rather, equals y plus 2. Now, if I go to my graph and actually graph these out, let me see what I get. So let me just get rid of what I've got in here, and I've got f of y equals y squared, which is both branches here. We only really want the top branch though. And then we have g of y equals y plus 2. And again, we're just looking for this region. Now, in order to see where these intersect, it looks like they intersect here at 4, 2, so 2 is the relevant part here when we do our limits of integration. So I'll say that f of y equals g of y at y equals 2. Now, in order to actually write this as an integral, I'm going to need the integral from y equals 0 to y equals 2. And then in here, I'm going to be doing rightmost minus leftmost function. So this is going to be g of y minus f of y. And I'm also going to have to put in not dx, but dy. Let's do that on the calculator and see what we get. So integral 0 to 2, parentheses. And what did we say? It was g of y minus f of y. Close all that, and then dy, and that comes out to about 3.333. For this next example, we're given f of x equals x squared, y equals 4, and we're just looking at the first quadrant part of this. And we want the volume of a solid of revolution when the area between these curves is revolved around the y-axis. No calculator on this one. Pause the video and give this one a shot. Alright, so if you were to graph this out, x squared is your basic parabola, y equals 4 is just a horizontal line through 4, so something like this. And if we're looking for the first quadrant, we're just looking for this area right here. So we're revolving this around the y-axis. And now that we've got all that, let's go ahead and get our volume by integrating this. So I'm going to need the integral, and I'm going to need y values. So we're going from 0 to positive 4. So integral from 0 to 4 of a of y. Now I can simplify this a little bit, and no calculator, so I'm going to need to. This is just going to be pi times y. Square root and square cancel each other out. So we have pi y dy. And now let me take the antiderivative of this. The y bumps up to a y squared. Dividing by 2, we have pi over 2 y squared from 0 to 4. So if we take out a pi over 2, and then we're just going to plug in 4 and 0 into the y squared inside of parentheses here. So we're going to have 4 squared minus 0 squared. And you could simplify it if you like. So this is going to be just 16 times pi over 2, which comes out to 8 pi. For this next calculator-based problem, they want us to write but not evaluate an integral for the volume of the solid of revolution for the area enclosed by all of these curves about the line x equals 5. Pause the video and see if you can come up with an integral for all this. And again, you can use the calculator on this for picture purposes. Alright, so let's see how that went. So on Desmos, let me just put these functions in here. So we have f of y equals square root of y over 2. G of y equals square root of y. Y equals 4. And the axis of revolution, x equals 5. And I'll just change the way that looks. Let me make it a different color. I think red is kind of nice if I can get to it. Let's try that again. There we go. And also make it a dashed line. So here's what I'm looking at. I've got this region in here, and I'm revolving it around this axis of symmetry. So because there's such a space between, any space, but this is a big space between the bounded region and the axis of revolution, we're going to need washers. So we need pi times big R squared minus little r squared. Big R squared is going to be whatever this curve is that's closer to the y-axis. We need to do 5 minus that to get that outer distance. Now, which curve is that? Is that f or y? Well, let me go back to Desmos, and these things are color-coded. This closer one here looks like that's the f of y function. So we're going to have pi times 5 minus f of y minus 5 minus g of y, all of that squared. And then to get the actual volume, we need to do an integral from 0 to, this is 4 up here, the line y equals 4, of just this a of y function that I had here. So a of y dy. For our final example, we'll do one of these cross-section volume problems. And this one, base of a solid is given by the region enclosed by this f of y and g of y function. So we have like kind of a quadratic and a linear sort of deal going on. Cross-sections perpendicular to the, here's the wording, to the y-axis. Our squares, they want us to find the volume. So again, this y-axis is tipping us off that we need to integrate with respect to y. So pause the video and try this one out, and this is another calculator one. All right, so let me start by graphing these functions on Desmos, and I'll need them in there anyway. So let's do f of y equals 4 minus y squared, and if you move this up here and zoom out a little bit, I don't need all these functions. There we go. This is a sideways parabola sort of deal. And then let's do g of y equals y minus 2. Put an equals in there. There we go. So it's this region in here. So we're trying to basically go from bottom to top and get some 3D squares coming out of this thing. So let's start by getting our area formula for these squares. In general, we've got sides squared. That's our general format for this a of y function that we're going to write here. And now to get the base of the squares, that's just the distance from the left to the right function. So we're basically going to have this f function minus the g function to give us all these horizontal distances. And then we'll square that subtraction. So f of y minus g of y squared. We also need to figure out the limits of integration. Looking at the graph here, it looks like -3 and +2 for the y values, the beginning and end of this. But let's just go on Desmos since we have it pulled open. And yes, down here we've got -3 for the y value. Up here is definitely +2. Cool. So we have f of y equals g of y at y equals -3 and 2. So we're just going to take the integral now from -3 to 2 of a of y dy. And let's go back to the calculator for all of that. So let me go down here, integral int, -3 to 2. And then, whoops, I do need to define my area function. Let me do a of y equals parentheses f of y minus g of y. Close that parentheses and square all that. All right, now that I've got that, I can do a of y in my integral, and that'll be a dy for that. Comes out to about 104.167. And that's it for that one. That's our volume. And that's it for the lesson. Thanks for joining me in paying our respects to y. Until next time, Mr. Sutton signing off.